Hey, welcome everyone to my channel. My name is Ansar, your helping hand, and today we're going to be doing or proving the central limit theorem. So this is basically the setup for the central limit theorem. There's actually a lot more setup, but this is the basic assumptions slash things that you need to have before you can use the central limit theorem. So basically you have these n independent and identically distributed random variables, and it doesn't matter what distribution they have, right? It can be any distribution. There's no specific distribution that needs to take on. It can be anything, as long as the distribution has a mean mu and a variance sigma squared, and both of those are less than infinity. Then the central limit theorem says that as n goes to infinity, that this standardized form of your sample mean will look like a standard normal. Remember, standardizing a variable means subtracting its mean and dividing by its variance, and in this case, this is what it's saying. Okay, so I have a whole video about the explanation behind the central limit theorem and why it's important. In this video, we're going to be proving it. Now, I want to mention that this proof, it's kind of, it's not difficult in the sense that the concepts behind it are difficult to understand. It's reasonably basic math or first year level math. However, it's in order to kind of get to the heart of the proof, right? We can either just start going from this statement over here and going about proving it, and then at each particular step, we're going to kind of be faced with this, what do we do now kind of situation, or what does this mean, or what is this equal to? And we could potentially go through, like, explain at every specific step what we need to go and do. But instead of doing that, I'd rather just go through all of the kind of little tricks that we're going to do throughout the proof beforehand, so that we can see where those tricks come from, and then we can just use the tricks or use the results of the trick in the proof, because the actual proof is different to kind of all of the manipulations that you're doing within the proof. Okay, so that being said, we're just going to kind of go through some of the prerequisite tricks and tips and things that we're going to be using. So the first thing is that this is the central limit theorem, like as we know it, right? That the limit of the standardized sample mean is a normal distribution or a standard normal distribution. Now that is equivalent to this statement over here. And the reason we need this equivalency is because we use the proof for this statement. And by proving this statement, you're proving the actual central limit theorem. So why is this statement true? Well, we can look at this little value over here, right? And we can see that, hey, it's okay, 1 over square root of n, and then we're summing up all of these, whatever we want to call these things. You can call it a standardized random variable. You're subtracting the mean and you're dividing by the standard deviation. So if we go and do that, we can say, okay, cool, this sigma over here, that comes out as a constant, and then we're just left with the sum of xi minus mu. And obviously we can take out the two sums or the two sigmas, so we can just have our xi's and we can just have our mu's. And then the xi's over here, we know that xn bar, or our sample average, is 1 over n of all of the sum of our xi's. So if we just want the sum of our xi's, this is equal to n times xn bar, right? And then this sum over here, well, we're just summing up mu n times, and mu doesn't depend on I, so we're just taking mu and we're adding it to mu, so that's 2 mu, and then 3 mu, and then 4 mu, up until n mu. So that line over there is equivalent to this, because the sum of our xi's is just nx bar, or xn bar, and then the sum of our mu's is just n mu, and then we can factorize the n out, and then once you factorize the n out, you can put it over the fraction, and that particular fraction over there, n over the square root of n, you can think of as n to the power of 1 over n to the power of a half, and then using kind of, exponent laws, that's just equal to n to the power of a half over 1, and so that's where that square root of n comes from. And then we have the square root of n times by xn bar minus mu over sigma is equal to this particular thing. So therefore, the limits of those two things are equivalent. So we have this statement over here, this equivalency. So that's the first point, is that this is the form of the CLT that we're going to prove. We're not going to prove that one. We're going to prove this one over here. And because these two things are equivalent, it's the same thing. Okay, now we kind of need to have this, there's this situation that we need to think about, which is this xi minus mu over sigma, right? The reason we define this new notation for it, so we're going to define some new notation for it, we're going to call it z, right? And the reason that we do that is because of the proof, and the proof essentially makes us do it. Well, not makes us do it, but doing this makes the proof easier to understand. You could do it without the proof, but you could do it without this kind of zi, but then you're just going to be working with less notation, and you're going to be having a kind of more cumbersome expressions lying around, and it's going to be less easy to see the proof for what it needs to be seen as. Okay, so zi is just whatever xi we have, and we subtract the mean and we divide by the standard deviation, right? So that's just one particular zi. So for every xi, for x1 we have z1, which is equal to, so it's not necessarily equal to, sorry, I shouldn't say equal to each other, but for every xi we have a zi, where zi is equal to xi minus mu over sigma, right? So for x1 we have a z1, for x2 we have a z2. So in this statement over here, where we're adding up from 1 to n of all of our xi's minus mu's over sigma, that's the same thing as adding up, so that's the same thing as this tn, right, where we have the sum from 1 to n of this xi minus mu over sigma. That's the same thing as summing up from I to n of all of our zi's. So therefore, the CLT can also be written as this particular thing, this particular statement, that the limit of tn over square root of n as n goes to infinity is a standard normal, and that's just literally tn we've defined to be this sum thing. Okay, so that's the second level of tips and tricks. The third level of tips and tricks before we get to the proof is looking at the expected value of zi. Now, expected value of zi is, well, using the definition of what zi is, it's xi minus mu over sigma. 1 over sigma comes out, and we're just left with e of xi minus mu. And using linearity of e of x, we can take all of those expectations separately, and then remember what we defined, well, not what we defined, but what xi is. Remember that xi is some random variable with a mean mu. What we're saying here is that e of x1 is equal to mu, and e of x2 is equal to mu, and e of x3 is equal to mu, and they're all the same thing until e of xn is also equal to mu. So that's the same thing as just saying e of xi, right? So that's where the mu comes from here, and then the expectation of a constant is just that constant because there is no randomness towards it, so it's always going to be equal to mu. And then we've got mu minus mu, so it's 0. So the mean of the z value is equal to 0, and we'll see why that's important later. And then we can also do the variance of zi. Now the variance of zi is the variance, using the definition of zi, is the variance of xi minus mu over sigma. We take this dividing by sigma out, but when you take out a constant from variance, it becomes the constant squared. So when we take out a 1 over sigma, it's going to become a 1 over sigma squared times the variance of xi minus mu. And then when you have a variance of a random variable, right, and you add or subtract a constant, because mu is a constant here, you're just left with the variance of the random variable, because the constant has no effect on the spread or the variation of the random variable. And then the variance of xi, using the same idea as the expectation, we said that the variation was sigma squared, so we have the variance of zi being equal to 1. Now, why is this important? Well, this is important because we need to know the moments of zi. And we'll see why it's important when we get to the proof. We still haven't gotten to the proof yet. We're just kind of in these are all the tips and tricks that we're going to be using in the proof, or we're going to be in the proof, we're going to have the moments, and we just want to be able to say this moment is equal to 0, this moment is equal to 1. So remember that the expectation of of zi is the moment generating function of zi. We take its derivative and we evaluate it at 0, and because we know that the expectation of zi is 0, we know that this statement is true. And then the variance of zi, right, isn't the variance of a random variable, right, of x, is not the second derivative of the moment generating function, because the moment generating function just gives you non-central moments. So what that means is that if we take the moment generating function of a particular value, of a particular random variable, and we take its second derivative, that's the same thing as this x squared, the expectation of x squared. So we have to kind of do some manipulation here to get to our second moment, our second non-central moment. And the way we do it is we say, well, the variance of a particular random variable is the expectation of that random variable squared minus the expectation of that random variable squared. So yeah, and then we would subtract, we would take this e of zi squared over to the other side, and we'd be left with this second moment, right, the second non-central moment of zi, and that's equal to the variance minus the expectation of zi squared, and the expectation of zi, which we saw earlier, or here, that's equal to 0, and the variance is equal to 1, so our second moment, our second non-central moment, is equal to 1. So we have mzi, the second derivative evaluated at 0 is equal to 1. Okay, that's great. Then the last moment-ish thing that we need is not really a moment, but it's just our moment generating function evaluated at 0. So this is the definition of the moment generating function for zi. You can obviously do it for other variables as well, but we need to know what it's evaluated at 0, and well, we just plug in 0 for t in the function, which means we're going to plug in 0 for t in the expectation, and when you do that, e to the 0, right, because 0 times zi is just always going to be 0, so e to the 0 is 1, so the expectation of 1 is 1. So we have this particular moment here, or it's not really a moment, but it's the moment generating function evaluated at 0, that's equal to 1. Okay, so that's kind of all of the tips and tricks that are going to happen in our proof. Now we need to actually get to the proof. So remember that the way that we're using the central limit theorem, right, our version of the central limit theorem is that the limit as n goes to infinity of tn, where this tn is just the sum from I is equal to n of zi, which is still just the sum from I is equal to 1 to n of xi minus mu over sigma. So our version of the CLT is this tn over root n is a normal 0, 1. Now, we've spoken before about the method of moment generating functions, and the method of moment generating functions is a statement about the fact that if you have two random variables and they have the exact same moment generating function, then they have the same distribution. And the same is true for the limit of moment generating functions. So basically, this over here, right, this central limit theorem, right, proving this is the same thing as proving that the limit as n goes to infinity of the moment generating function of tn over root n right, of t is equal to the moment generating function of some, I can't call it z because I already have z, of some y variable, right, of t, where y is a normal 0, 1. Okay, so these two things are equivalent, right? These two proofs are equivalent because of the way that moment generating functions work. So now we can actually start with our proof. So this is the proof. Okay, so the right-hand side, right? The right-hand side of this statement is the moment generating function of y. And because we know that y is standard normal, this is just e t squared over 2. So this is just the moment generating function of y. And now we need to show somehow that the limit as n goes to infinity of the moment generating function of tn over square root of n is e to the t squared. So how do we go about doing that? Well, we need to kind of first consider what is mt root n of t. What is that equal to? That's the expectation using the definition of moment generating functions. That's t times, and now it's going to be a bit weird because we've got this small t and we've got this big T, but just remember that the big T is the random variable, which is that sum that we defined earlier, and the small t is just the argument for the moment generating function. So this is equivalent to e of e t over root n times tn. Okay, I've just moved this square root of n over to the other side, or not over to the other side, but just moved it over, and it's a product, so you can do that. Now we need to look at what tn is equal to, and if we look over here, we'll see tn is just the sum of zi's from 1 to n. So this is t over root n times the sum from I is equal to n of zi. And now we have that this can be written as t over root n times z1, right? And I could write plus here. I could write plus in the exponent, but what I'm going to do is I'm going to actually bring it out and write it as t over root n z2, because remember, when we multiply the same base, we can add the exponents, so that's going to be equal to e t root n z3, and then all the way to e t over root n zn. Okay, so now we had this assumption that all of our x1, x2, and ... xn, we had the assumption in the central limit statement that these were independent, right? Which means that any function of those random variables will also be independent, and because they are independent, we can take the expectation of the products as being the product of the expectations. So that's going to be root n z1 times e of e t over root n z2 ... times by e of e to the t over root n zn. Okay, now, right, if we look at this, all of these by themselves, these all look like the moment generating functions of z1, z2, z3, zn, right? And they're being evaluated at t over root n, okay? And because all of these are identically distributed, the moment generating functions are going to be identically distributed, so we have, this is the same thing as the moment generating function for one of the zi's, right, or any of the zi's, doesn't really matter which one we choose, evaluated at tn over root n, and then that's all to the n because we're multiplying it n times. So this is the moment generating function of tn over root n of t, right, is just equal to one of the zi's evaluated at t over root n to the power of n. And now we need to take the limit of this thing as n goes to infinity, okay, root n t. Well, because we know what this is, this value over here, we can write, okay, this is the same thing as the limit as n goes to infinity of this value over here, which is zit over root n, and then to the power of n. Now, we do need to know our limit laws, and the way our limit laws work is, well, what you do is you kind of plug in the limit and you see what happens, and because this is a continuous function, we can do that. So essentially what's going to happen is, as n goes to infinity, we have this t over root n. As n goes to infinity, root n goes to infinity, and because we're dividing by infinity, a constant divided by infinity, right, this is going to go to 0, okay, and then we know from earlier that the moment generating function of zi evaluated at 0 is equal to 1. This is why that was important. So this is going to be 1, right? This inside is going to be 1 to the power of infinity, okay, as n goes to infinity. Now, that's what's called an indeterminate form, which basically, well, it's a version of the indeterminate form that once we do some manipulation on it, we can use Lhopitals rule. So Lhopitals rule, we can't really do anything with it at the moment, but if we take the natural log of tn over root n of t, okay, that's going to be the same thing as taking the natural log of this thing. And if you take the natural log or any log of something to a power, that power is going to come out, n times the natural log of zi over t root n. Now, when we take the limit of this and the limit of this, right, we will get something that's easier to work with, right, and hopefully we'll be able to use L'Hopital. And once we've evaluated the limit, we just have to take e to both sides, and then we're going to get what, or we can kind of think of this as the log of the limit, and the limits come out. But essentially, what I'm saying is that we're going to take the log, we're going to evaluate the limit, and then we're going to take e to whatever we found whatever the limit was evaluated to. And that's kind of, I mean, that's more like, you know, maths 144 information. I'm not going to go over that, but that's just a recap of how this works. So if we now take the limit of this, of as n goes to infinity, of n ln m zi t over root n, okay, this is going to be infinity, right? So it's going to be n is going to be infinity, and then over here, remember that this is still going to go to 0, and the moment generating function evaluated at 0 is still going to be, evaluated at 0 is still going to be 1. So we're still going to have 1 here, right? So what I'm saying is the moment generating function evaluated at 0, which is what happens to this argument as n goes to infinity, is still 1. The natural log of 1 is 0, so this is going to be infinity times 0, which still isn't an indeterminate form that can use Lhopitals rule, but it can still work if we take the n, zi t over root n, if we take the n here. So this is going to become n minus 1. So now, if we look at this, as n goes to infinity, right, this goes to 0, the argument of the moment generating function goes to 0, the moment generating function at 0 goes to 1, and then the natural log of 1 is 0, so we've got 0 on the top, and then as n goes to infinity, 1 over n goes to 0. So we have 0 over 0, so now we can do Lhopitals rule, but there's kind of this little issue, which is just that our n value, right, that's our sample size, right? That's an integer. It's either 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up until infinity, but it's an integer. It's not a real number. It can't take on 0.5. We can't have a sample size of a half or a sample size of 3.5 or whatever, right? So we can't really take derivatives of things, which is what we need to do when we do L'Hopital's rule. So we kind of need to redefine this limit thing. So what we're going to do is we're going to say, okay, y is equal to 1 over root n, okay, and y is a real number now. So we're defining y to be some real value, and we're defining it to be equal to 1 over root n. Now, as n goes to infinity, right, this denominator is going to go to infinity, and a constant over a denominator goes to infinity, means that y goes to 0. Okay, so now we can rewrite this limit as n, sorry, not as n, but as y goes to 0. Sorry, I know my handwriting is getting worse. So the natural log will stay the same. The moment generating function stays the same. The inside of the moment generating function, the argument, however, is no longer 1 over root n times t, or t over root n. It now becomes y of t. Okay, and the bottom part, well, if y is equal to 1 over root n, y squared is equal to 1 over n, because we're going to square both sides, so that, which is n to the minus 1. And that's what we have at the bottom. So now we have y squared. And now we still have 0 over 0. It still goes to 0 over 0. It doesn't really change that. But now we can do Lhopitals rule. Now we can actually apply Lhopitals rule. So we can take the derivative of the top and of the bottom. And now we're going to use our derivative laws that I assume you guys all know. So we're going to use the chain rule quite a bit at the top. And the chain rule says that when you take a composition of function, the derivative is equal to the derivative of the outside function with respect to the inside function multiplied by the derivative of the inside function. So the derivative of the outside function, the log, with respect to the moment generating function is just 1 over the moment generating function. Now, I'm going to do this in two ways. If I have 1 over the moment generating function, that's just going to mean the moment generating function is going to go to the bottom of the fraction. So I'm going to have zi of yt, right? And then I have to multiply by the derivative of the inside. Well, the derivative of the inside, once again, is a function, and it's not just a function of y, it's a function of a composition of y, because I have to take y multiplied by t, and then I put that into the moment generating function. So what I'm going to do is I'm going to apply the chain rule again, and we're going to have the moment generating function derivative with respect to the composition, so the y of t, and then multiplied by the derivative of the inside. The derivative of the inside with respect to y is going to be y times a constant. The derivative of y times a constant with respect to y is just the constant, so it's just t. And then I have to take the derivative of the bottom, because this is what L'Hopital is, and that's just going to be 2y. Okay, so now we have to think about what happens to our moment generating functions derivatives when we go to 0, and this is why those moment generating function questions or tips and tricks were important. So we saw earlier that the moment generating function evaluated at 0 is just the expected value. The first derivative of the moment generating function evaluated at 0 is just the expected value of zi, and the expected value of zi is 0. Okay, so I'm going to have 0 at the top, okay, and then at the bottom, well, this is just going to be y goes to 0 is going to mean the bottom's also going to go to 0. Okay, so I'm going to have 0 over 0 again. I should look at what this mzi, the moment generating function, what this goes to. This goes to 1 as y goes to 0. So because of that, as a limit, well, the limit laws mean that I can take out, I can separate fractions. So the limit of a fraction is equal to, the fraction of the limits, and the limit of a product is equal to the product of the limits. So I can basically say this, well, this is equal to the limit as y goes to 0 of 1 over mzi of yt multiplied by the limit as y goes to 0 of mzi yt, the derivative of mzi times by t over 2y. So I'm just kind of splitting out this part over here, but this part over here, right, as y goes to 0, that means the argument's going to go to 0, and the moment generating function evaluated at 0 is just equal to 1, so that's just equal to 1. So we kind of get rid of this particular thing, and then we have this little nasty thing over here, but that also, once again, just goes to 0 over 0, because as y goes to 0, right, the inside of the first derivative of the moment generating function is going to go to 0. So I'm evaluating my moment generating function's derivative at 0, which is just the expected value of zi, which is 0. So that's the top's going to go to 0. And the bottom's also going to go to 0, because y goes to 0. Y going to 0 means that 2y also goes to 0. So then I have the Lhopitals rule. I have to do Lhopitals rule a second time. So then I take this another derivative, right? So that's times the limit as y goes to 0. So now I'm doing this, I'm going to take the derivative of this function, which once again is the chain rule. And the t part over here, that t is just a constant. So I don't really need, that's just, yeah, that as a derivative, the constants come out. So this is going to be zi double prime yt. But now remember that this is a composition, so I need to take the derivative, right, of the outside function with respect to the inside function, and then multiply it by the derivative of the inside function with respect to y. And the derivative of the inside function, yt, with respect to y is just t. Okay, so that's the top, the numerator. And then the bottom, while the derivative of 2y with respect to y is just 2. Okay, and now we're getting somewhere very, very close to what we need to be, because now this is just y, the limit as y goes to 0 of t squared multiplied by zi double prime of yt over 2. And using our tips and tricks from earlier, we saw that when we take the moment generating function and we take the second derivative and evaluate it at 0, that's equal to 1. So as y goes to 0, this part over here, this moment generating function, is going to go to 1. This t squared over 2 part, that doesn't depend on y, so that's going to be t squared over 2, right, multiplied by 1, which is t squared over 2. So now, where this whole thing came from was that we were taking the log of our moment generating function of tn over that's root n over there, right? That's where this t squared comes from. So we have the limit of m t, sorry, that's a t, n over root n of t is equal to t squared over 2. So then in order to get rid of the log, we take the exponential. And when we take the exponential of this, we're just left with tn over root n of t, right? And we're left with e t squared over 2. So now we've proven that the moment generating function, or the limit, because this is what we were doing when we did all those limits, is we were actually taking the limit as n goes to infinity, right? As n goes to infinity. We were taking the limit, so we now know that the limit as n goes to infinity of the moment generating function of tn, the sum of those zi's over square root of n of t, is equal to e to the t squared over 2, which is equal to our left-hand side, right? Our left-hand side, the proof that we were trying to prove, remember, is, sorry, there's a lot of things, is that. That is what is our left-hand side, and that's equal to our right-hand side. So therefore, we have shown that the left-hand side is equal to the right-hand side, and so therefore, we've shown that the CLT is true. We've shown that essentially the limit as n goes to infinity of tn over square root of n, that is a normal distribution 0, 1, and based on what our definition of tn was, this is the same thing as 1 over square root of n summed up from I is equal to n of zi's. Tn's was defined in terms of zi's, but zi's is just equal to xi minus mu over sigma, because that's what we defined our zi's to be. And then we showed earlier that this statement over here is equivalent to the limit as n goes to infinity, sorry, that's a horrible thing, of the square root of n times xn bar minus mu over sigma is equal to a standard normal. Okay, so that is the proof for the central limit theorem. Obviously, it is a very, very long proof, but it's also a very, very powerful result. So we can't really get a powerful result without some kind of effort. So yeah, that is the proof of the central limit theorem. Please remember to like and subscribe. Comment if you have any questions. Comment if you have any requests. And yeah, I'll see you in the next video. Bye.